course project, really, right? And it's clear that it's a straightforward thing. So things have advanced quite rapidly, both in terms of people's acceptance and understanding of AI and the actual functionality of AI systems. But I think we're still not there yet to the level of AI systems like you see in science fiction movies. Like this AI in Star Trek was this, it looked like a metal box, like a, I don't know, food processing machine or something, but it was in, you know, it was traveling around the universe in its own spacecraft, exploring new planets and acting as its own sort of autonomous agent, charting its path through the cosmos, right? We don't yet have AIs that can act as their own autonomous agents and try to adapt to whatever new situation that they find themselves in, which is what I refer to as artificial general intelligence, AIs that can fundamentally generalize beyond their experience base and their programming and sort of take leaps of creativity to adapt to the unknown. And we're in some ways getting closer and closer to that goal, but in some ways, you know, we're still quite far, and that there's a big breakthrough, I think, between here and AGI. You know, I introduced the term AGI for the first time, I think, in 2004 with a book called Artificial General Intelligence, which had a bunch of papers outlining different approaches. And I've organized the conference series on AGI every year since, I guess, 2006. There's been a diversity of approaches to AGI in the research field, some of which I'll talk about today. But the other thing we've seen in the last few years is one particular approach to AI based on deep neural networks has gotten a huge amount of practical success in certain things, and then a huge amount of popular notoriety. And I mean, the latest incarnation of this is ChatGPT, which is sort of taking the world by storm, and which I'm not sure will seem that significant in a historical sense looking back, in that I think the main innovation there was transformer neural nets, which were really created at Google Brain and first came out in the BERT model from Google. And now that ChatGPT has gotten the public eye, there's going to be many more and better systems created by OpenAI and by others during the next couple years. But still, you know, ChatGPT is interesting at the moment in that it's sort of it's the first AI system I've seen that has sort of you know, grabbed the world by the throat and made people say, wait a minute, maybe these machines really are going to become as intelligent as people are. I mean, it's quite far from a human level intelligence, as you see after chatting with it for a little while. In some senses, it fundamentally has no idea what it's talking about, and it can. Oh, okay. It can get some things wrong in ways that people never would. On the other hand, it is in some ways remarkable in how it can sort of synthesize information to give intelligent-looking responses. Let's see. Operating these slides is straining my own general intelligence. Give me a moment. There we go. All right, great. So what I think that the deep neural nets behind ChatGPT and other similar systems are very, you know, they're very interesting and powerful in themselves. Not necessarily ChatGPT itself, but I think other successors of that technology really are going to eliminate a significant percentage of white-collar jobs that people do now. And similar technologies integrated with robots will eliminate a lot of blue-collar jobs in manufacturing and service industry and so forth. So I think even this technology, for all its narrowness, and it's not being general intelligence, I mean, it still can have a revolutionary impact on the world. I mean, let's say over the next 5 or 7 years, 50 or 60% of humans are out of work because AI and robots can do all their jobs. I mean, even though we haven't reached AGI yet, that's quite a major disruption to economy and society. But I also think that these deep neural net tools that we see behind ChatGPT and similar programs, I think these can be a significant component of an AGI system, even if they're not themselves capable of AGI. And so one of the things I want to talk about today is how I think you can maybe get to AGI by putting together deep neural nets with logical reasoning systems. And this gives you what's called a neural symbolic approach to AGI. And of course, no one really knows how we're going to make a breakthrough toward human-level general intelligence. Some people think you can get there by sort of upgrading and tweaking current deep neural nets. Certainly the guys at OpenAI think that. Other people think you need something utterly different than anything anyone is working on now. Like you need a quantum computer, you need to grow a brain in a vat, or you need some totally different kind of algorithm nobody has ever thought of, right? And all these, you have to say, are still possible because we haven't solved the problem yet. So my bet is somewhere between these extremes, that the deep neural nets are a valuable component for statistical pattern recognition and synthesis, but don't do everything that you really need for a generally intelligent mind. And I'm going to explain a little bit about why I think that, and what I think is coming in the AI field. And this talk is pretty high level and sort of hand wavy. I'm not going to go into deep technical details, but I will point out where you can look online if you want to find more technical details. So looking very crudely at the long history of AI, I mean, you could really trace AI back to the 1930s or 40s with Norbert Wiener's book, Cybernetics, the control and communication in man and machine. And I mean, the first papers on neural nets came out, I guess, late 1940s by McCulloch and Pitts, where they showed that artificial neural nets were Turing-complete computers. So and they started building artificial neural nets with vacuum tubes, right? So I mean, this has been around a while, and you had a bunch of different AI methods being explored back then in the 50s and 60s, which is before my time. I mean, I was born in 66, but I mean, you had then people using, they beat the game of checkers in the late 60s, for example, which was a big deal at the time. They made the first computer algebra systems, which are now not even considered AI. They're just tools, but what you see in programs like Mathematica and MATLAB and so forth. Neural nets were one of the tools being explored then. They became unpopular in the 1970s, I guess because people were making too much hype, saying they were going to do everything they're doing now, basically. But people were saying it in the late 60s and early 70s, and people stopped believing them. Neural nets became unpopular. Symbolic AI rose, and you had what was called expert systems. But this was a pretty silly approach, really, where people tried to encode in a logic language a rule for everything the AI had to do. You know, like if you come up to a microphone and want to speak, turn it on. If you want to speak, open your mouth, right? If you want to step, first lift one leg up, then put it down. And trying to specify as a rule everything a system needs to do, I mean, that in some sense it could work, but you would need like quadrillions of rules or something, right? I mean, it's not practical. There was a project called Psych that coded many millions of rules, coded by like 50 people just typing in rules day after day, but it's not really a workable approach. You had also something called genetic algorithms or evolutionary learning, where you try to simulate evolution by natural selection, and that's quite interesting. It's a very creative method, and you could design artwork, you could design circuits. A number of patents were made by people using evolutionary algorithms to design new circuits and other things. But what really broke AI through, of course, was neural networks, which really coincided with the rise of the internet. I mean, the internet gave us so much data, and the internet brought us an upsurge in video gaming, which brought us GPUs, which then turned out to be really good for the matrix multiplications involved in AI, right? So then with the internet, for all these reasons, neural nets trained on huge amounts of data started to rise to the fore and to do amazing things. And we saw, like, from 2014 to 17, computer vision transitioned from being a research corner to a major part of industry, and from 2018 till now, the same has happened with natural language processing. Now, what happens next? What happens next is not known. My own hypothesis is we're going to integrate neural, symbolic, and evolutionary AI to get to AGI. As I said, some people think neural nets will just be upscaled. Some people think all this is barking up the wrong tree. So what do current neural nets not do well? I mean, we see what they do well with Stable Diffusion, ChatGPT, and other systems like that, and with neural nets for, say, classification, for identifying what's wrong with your lungs from a radiology image and so forth. So we see a bunch of things that neural nets can do well. What do they not do well? When used for synthesis of language or pictures, they make a lot of weird stuff up, right? And in images, it's just kind of funny. They make up a soccer player with 3 legs because they seem to know that people have 2 legs. For of course, medical question answering or something, it would be very bad because you don't want a fake medical diagnosis or them to tell you to drink bleach like Donald Trump or something, right? So I mean, there's hallucination and confabulation, and an issue there is the system doesn't know when it's making stuff up. Like, it's cool to make stuff up, that's fine, that shows artificial creativity, but not knowing when you're making stuff up or reported something that was observed in the world is a problem for many applications. It's not for making graphic art, it's not a big problem. A person can just look at the picture and use it or not. Self-inconsistency goes along with confabulation. I mean, you could ask the same question in slightly different ways, and you'll get weirdly different answers. Again, sometimes that's fun. Like I play keyboard in a band. The robot lead singer generates her lyrics by AI, and if she generates weird random stuff, that's fine. And if it's different each time, that's cool, right? But again, for some cases, that's problematic. There's no ability to do complex reasoning, and there's no fundamental creativity, and that is worked around to some extent by having such a huge training database, right? So a real AGI system can do a wide variety of things, not because it was told exactly how to do all those things, but because it's making a leap beyond its experience. Like how I learned to use the internet, right? It didn't exist when I was born or when I went to school. You just put in front of you, and you got to muck around and figure it out. A system like ChatGPT can do a great variety of things, but it gets that generality just by having a very general training data set. Like, it read virtually the whole web. There's so much on there, and then it learned how to respond to all those things. So that's a cool trick for letting you do a great variety of things without being able to reason much and without being fundamentally creative. On the other hand, it does run dry, right? Like, if you had a world population of 8 billion ChatGPTs, nothing new would ever get invented because it's just recycling what was there before. Now, one thing it does is expose how repetitious and boring most human jobs are, right? Because you can obsolete most human jobs without coming up with anything new and without much reasoning, just by repeating back stuff that was done before. But the fact that will do most human jobs doesn't mean that exhausts human intelligence. It just means that human jobs do a disservice to human intelligence, right? So so these issues are well understood. What's not agreed is how do you overcome these issues, right? And that's the, to me, the biggest fundamental research problem in AI today. I mean, there are many other interesting research problems, like, how do you customize current existing AI systems to do this or that practical application? So for example, to control a robot to have a conversation, or I'm applying machine learning and machine reasoning to analyze DNA data from long-lived organisms to understand longevity. There's loads of cool application projects like that, but at the core of AI technology, overcoming these issues is probably what we need to do to get from here to general intelligence, because we have a lot of stuff already working now, even though these things don't work, right? And so it's a quite interesting position to be in. So just as one example, one of my friends asked ChatGPT rather, which is made by the company OpenAI, asked it about SingularityNet, which is my own blockchain-based AI platform. What ChatGPT said is that SingularityNet and OpenAI were both co-founded by Dr. Ben Goertzel. And this was amusing for me to notice, because I actually had nothing to do with OpenAI. What was funny is that ChatGPT, that was created at OpenAI, thought in some sense that I founded the company that created it. But I mean, of course, it read OpenAI's website. It knows that's not true in some sense, right? But in another sense, it doesn't know anything. It's just piecing together stuff that seems related in the context of whatever query it was asking. That's going to be hard to read on this screen, but this was a bunch of questions posed by Andrew Ng, one of the founders of deep learning. He asked a ChatGPT system, why is CPU computation faster than GPU computation for deep learning? Why is DNA computing faster than CPU computation for deep learning? Which is totally not true. I mean, DNA computing is incredibly slow. Why is abacus computing faster than DNA computing for deep learning? And each time it will come up with an answer. Abacus computing is generally faster than DNA computing for deep learning because it uses the principles of mechanical computation. And this, I mean, if you don't know anything about it, it sounds very convincing and compelling, right? So it's funny. No one foresaw that one of the first really successful AI applications was going to be just coming up with compelling sounding nonsense, right? Just BSing people. And I mean, it's impressive. I mean, people get a lot of sales training to learn to BS people, right? I mean, it's an art, but it's not the art that we thought AIs would first learn. On the other hand, when you consider this is an AI that's digested the whole internet, there's a lot of BS on the internet, right? So, I mean, it's also not surprising that that's what you'd learn after reading the whole internet. So the underlying weaknesses here, I think, are we're doing statistical pattern recognition and generation. We're just looking at what's out there and figuring out how to combine it. We're not abstracting or forming concepts explicitly or implicitly, and the system doesn't know what or who it is and what or who you are, right? And I mean, it's interesting you can get so far without any of these things. It's also doubtful to me you can really get to human level or human-like general intelligence without these things. No, that's a little too fast. Where were we? Okay, there we are. So there's a number of ways to conceptualize what is intelligence, and it may be that having a full sort of definition of what is intelligence doesn't even matter. Like biologists don't have a clear definition of what is life, and the fact that a virus is sort of life and sort of not life doesn't really matter. It's no objection to doing synthetic biology and making organisms either. So I mean, precisely defining intelligence, I don't think it's actually necessary for building intelligence. It's still interesting though. I mean, Marcus Herter, who's a mathematician and AGI researcher, now at Google DeepMind, he wrote a book called Universal Intelligence, which gives a math definition of general intelligence, which basically comes down to the ability to maximize computable reward functions in computable environments. Like on average, over all computable reward functions in environments, how well do you do it at achieving that reward function in that environment? And by that criterion, humans are very, very stupid, right? Like I can't run a maze in 750 dimensions. You know, I can't even figure out how to click the slides back and forth. So clearly I cannot optimize all computable reward functions in all computable environments. I mean, as having taught university for some number of years, I realized like half of students couldn't figure out how to do differential and integral calculus even, right? So on the other hand, there's still a sense in which we're more generally intelligent than like a rat or a monkey or a dog or a rock, right? So a different conception of AGI is given in the PhD thesis of my friend Weaver, David Weaver, and he has a notion of open-ended intelligence. He's trying to view intelligences as complex, self-organizing systems which are driven by two goals. One is survive, like individuate, maintain your boundaries as a system, maintain continuous existence as a system. The other is to self-transcend, to keep exploring and doing new things which obsoleted your previous boundaries. And you can formalize these just as you can formalize things about reward functions. So I would say, if you look at this conception of intelligence, which is a little more biology-oriented, commercial neural net systems today just are not trying to do these things. I mean, they don't have to survive. They're not trying to maintain their boundaries. They're not trying to grow and learn either. They're just kind of different, a different sort of thing than an open-ended biological intelligence. No. The mouse, oh, maybe. It seems to be buffering the clicks for than doing them all at once. Yeah. Let's see. Okay. Does the mouse actually work? No, the mouse does something else, doesn't it? Ah, use the wheel on the mouse. That's it. All right. All right. So what do we need to get to human level AGI? We've talked about what's missing. What I think we need, you do need the ability to recognize and generate patterns, which is what current neural nets are doing well. I mean, obviously we do that. We recognize and generate patterns. And actually, we often do it without knowing what we're talking about, just like a neural net does today. Like my 1-year-old daughter last night, or the last night I was home before coming here, tried to get her to go to sleep. She's like, I don't want to go to sleep. Sleep is boring. And I know she doesn't know what boring means, right? She heard someone say sleep is boring, and she figured that was an appropriate thing to say. And that's, I mean, that's sort of like ChatGPT does. It's synthesizing something that sounds plausible given the context, and that. You know, she says that, she sees how we respond, and then she learns something. So we do need to do pattern recognition and generation, but we also abstract in a way that current neural nets seem not to. And this relates to the huge number of parameters in current neural nets, right? Because I mean, you have many billions, tens, hundreds of billions of parameters. And I think being that big is not necessarily good. I mean, I think the more you've abstracted, the more compact your knowledge base can be actually. And if you need to have a really, really huge collection of data, that means you're probably not doing that much abstraction. And then, I mean, if you look in statistical learning theory, there's a something called minimum description length principle, right? Like compacting something smaller, a more compact description generalizes better beyond its training data. Now, of course, there's more subtlety than that. You could have a very large model that generalizes well under some circumstances. But I think one way or another, you need to come up with concise, abstract, approximate summaries of your experience, rather than just having a huge list of special cases in your mind. And we ground patterns, abstractions, we ground linguistic patterns in observations, right? So like when my 1-year-old says sleep is boring, she knows what sleep is because she knows she sleeps. And eventually she'll learn what boring is because she'll hear us say, like, waiting in line in the airport is boring or something. And then the grounding of the words in non-linguistic experience certainly gives nuance that you don't get just by connecting words to each other, which ties in with the ability to distinguish truth from nonsense, right? Because if you're not grounding anything in non-linguistic experience, it's very hard to distinguish truth from nonsense. Creating fundamentally new things, we know how to do that in a way because evolution does that. We have evolution of species. We have the evolution of life from bubbling clay pools on the early Earth, right? So it's clear that evolution, which combines pieces of one thing with pieces of another thing and mutates it, it's clear that this is an engine of creativity. And there's a theory called neural Darwinism from decades ago that explains how the brain can do evolutionary creativity by a sort of natural selection among neural assemblies, right? So I mean, we know how creativity can work, and there's been neural nets that do evolutionary learning. It's not how current deep neural nets are operating. It's a different sort of way of organizing a neural net, and I think you do need something more evolution-like inside your AI mind to get creative improvisation. And reasoning also plays a role. I mean, most people don't reason that elaborately in their everyday lives. On the other hand, if you're going to prove a math theorem or create a new biological hypothesis or build a machine, you're carrying out long series of reasoning steps. And this also comes up in other contexts. Certainly it comes up in military strategy. Even if you're fencing, if you're sword fighting, you're planning 5-10 steps ahead, and you're carrying out a lengthy reasoning chain. And this is something current neural nets don't do. It's quite important. Understanding yourself and the other person you're interacting with, the other mind you're interacting with. I mean, clearly, this is what psychologists call theory of mind modeling, right? We model what's in the other person's mind, and then we learn something about their reactions from that. And finally, there's the capability to develop, to fundamentally change yourself. I mean, in psychology, we distinguish learning from development. Learning, you're basically keeping yourself the same, but you're gaining new skills and abilities. But I mean, like between age 2 and age 56, which I am now, I haven't just learned new skills. Like my whole way of thinking and being has changed a few times in that interval, right? So we're developing, we're continuously morphing ourselves into fundamentally new systems that have some resemblance to our previous version. And this requires an ability to modify and improve ourselves. Now, again, humans are limited at that. Like, I don't know how to refactor my dopamine receptors or something, right? So I don't know how to change the way my glial cells work. So we have some things we don't modify, but there's a lot of developmental plasticity over the human lifespan compared to current AI systems, which each system has its fixed architecture. And then you do an upgrade, like you throw out GPT-3 and get GPT-4. But GPT-3 didn't progressively morph itself into GPT-4 or something, whereas humans do develop in that way. So these things are all needed, and we have some understanding in the AI field how to do each of these, and there are prototype systems and loads of research papers on each one of these things, but none of them has been put all together into one practical AI system actually doing stuff, right? And there's a lot of possible approaches to breaking through this barrier and getting general intelligence to really work. My own approach is now centered on a software system called Hyperon, which is a new version of a system called OpenCog. So OpenCog, my colleagues and I started building in 2008 based on some code that went back to 2001 or something. We decided 2 years ago to refactor the OpenCog code base into a new system, which we're working on now. The theory underlying this is fairly deep, and I won't go into in too much detail, but there's a paper on archive.org that I wrote called The General Theory of General Intelligence. And if you look at that paper, you can see the cognitive and math and computer science theory behind this. And there's a series of, like, I don't know what, 10 videos on YouTube I recorded stepping through that paper almost line by line. So the core conceptual notion, you're viewing a mind as a system that recognizes patterns in itself and the world, including introspectively recognizing patterns in what it has done or should do to achieve certain goals in the world. And the core data structure there is a big knowledge metagraph, which is metagraph. It's sort of like a graph in the computer science sense, but you can have links pointing to links. You can have links going between 3 or 4 nodes instead of 2 nodes. You can have links pointing to whole subgraphs, so it's a slightly generalized graph. So we have this knowledge metagraph. It lives in RAM on multiple network machines. It also lives in a backing database on disk. And we represent both knowledge and learning and reasoning algorithms. They're all represented in this knowledge graph. So both the algorithms and the data, the program and data, are all the same. They're in the knowledge graph. And then parts of the knowledge graph are active, and they act by transforming the knowledge graph. And then you have neural net algorithms in this vast self-organizing graph. You also have probabilistic logical reasoning algorithms. You have evolutionary algorithms. But all the algorithms are parts of the graph that are engaged with rewriting parts of the knowledge graph. And so this is OpenCog system, and there's 2 key technical components. One is the knowledge graph is called the atom space, and the nodes and links are called logical atoms. There's a distributed knowledge graph component. Then we've developed a new programming language called Meta, which is stands for Meta Type Talk, which is basically a programming language designed to compile into a graph to make parts of the graph rewrite other parts of it. So for computer science programming language geeks, it's a fairly abstract language, which is, I guess, a probabilistically, gradually, dependently typed language. So if anyone ever played with weird languages like Idris or Agda, it's sort of a next step beyond that in use of dependent typing. Which is a sort of language that not many humans are going to want to program in, but it's mostly, we're programming in it, but it's mostly intended for the AGI to be reprogramming itself, right? So it doesn't need to be that human friendly. Oh, okay. So yeah, this is a rough diagram of this particular AI system. I mean, the SingularityNet platform is a blockchain-based sort of deployment layer that lets you run all this stuff distributed across many different machines with no central controller. So the blockchain is used to allow decentralized coordination of many machines in the infrastructure. Then you have the atom space, which is shown to the right. You have the language interpreter for the meta language, which is called Atomese there. And then various AI algorithms shown on the left, neural net libraries, probabilistic reasoning, evolutionary program learning. And for neural networks, we're not running every neural network inside this knowledge graph. So we can run a neural network in PyTorch or whatever toolkit you prefer, and then we can interface that with the Hyperon system. And if you have worked with PyTorch or things like that, in PyTorch, you have explicit access to the computation graph. So you can take the compute graph of PyTorch and you can pull it into the knowledge graph in OpenCog and manipulate and reason on it, and then modify the compute graph and export it. So we're taking this knowledge graph manipulation and reasoning system, and we're like hybridizing and connecting it with neural models written in modern neural net toolkits. So one example, which I don't have a slide on, but I'll just mention it. One example we're working with, you can take a large language model. It could be ChatGPT. We're not using that. We're using our own large language model because we wanted free API access at unlimited amounts. But you can take a large language model of that nature. You can then use certain methods to extract logical knowledge from it. So you basically use few-shot learning to train the large language model to output predicate logic formalizations of what it knows. So then when you've gotten the language model to export logical versions of what it knows, then you have a large logic knowledge base representing what the language model learned. You feed that into your reasoning system. Then you can do generalization. You can do inductive, abductive, deductive reasoning. You can spot inconsistencies. You can then take that logical knowledge and you can use that logical knowledge to fine-tune the language model based on what the inference engine concluded, right? So you're interfacing the symbolic model for reasoning with the language model for pattern recognition. And there's a lot of different things you can do along these lines. I think this computer is running Windows 3.1. It's very slow. Or not? All right. Okay, so there's a lot of depth in that previous slide, and if folks have a AI or computer science background, maybe if you ask questions after the talk, we can go into that more. But I mean, there's a fair bit of math and engineering there, which is hard to go through rapidly. I want to talk a little bit about scaling up now. So, neural nets were invented in the 1940s as a math and computer model of what happens in the brain. I remember teaching neural nets in University of Western Australia when I was an academic in the computer science and cognitive science departments. Would have been 95, 96. We were doing recurrent back propagation. You had a neural net with maybe 30 or 40 nodes, and training it would take literally all day on the machines at the university, right? So, and you could do some interesting things. We had it, conjugating verbs and so forth, and it could doing a little bit of automatic handwriting recognition. It was doing something. The deep neural nets we have now they're a bit different, but they're not fundamentally different from the deep neural nets we were training them with recurrent back propagation, right? I mean, the biggest difference is we can just do, like, instead of, 30 neurons with a few hundred parameters, you have a few 100 billion parameters now, right? So, like, where's this come from? Well, it came from the internet, and it came from GPUs and massive multi-GPU server farms and so forth. So that having the right infrastructure helped tremendously in making these sort of same old algorithms do really cool things. And in a way that was luck, because GPUs were really invented for rendering computer graphics and video games, right? And then people found, well, wait, they also work for scientific computing. So it's partly that's the story of the power of mathematical abstraction, right? Because computer graphics and neural nets, it's all matrix multiplication. So as long as you can use your matrix multiplication libraries, it'll be fast. Now, symbolic AI, graph-based AI, evolutionary AI, doesn't necessarily boil down to matrix multiplication. And so the hardware infrastructure that has allowed neural nets to accelerate so tremendously doesn't so directly apply. You can certainly do it. You can use GPUs to accelerate graph-based and symbolic evolutionary AI methods, but it doesn't provide the same payoff it does applied to neural nets or rendering of graphics. And if you get into parallel architectures, at the base level, there's something called SIMD, SIMD architectures, which is single instruction, multiple data stream. Then there's something called MIMD, MIMD data structures, which is multiple instruction, multiple data stream. And roughly in SIMD parallelism, you have a bunch of processors, but they're all doing the same operation at the same time. In MIMD parallelism, you have a bunch of processors which may each be doing a different thing at the same point in time. And of course, the brain is not synchronous. The brain is MIMD parallel. Different parts of the brain are operating at different speeds and sending different neurotransmitters around and so forth. I mean, biological systems are kind of a mess, right? But an artificial neural net, you can boil down to matrix multiplication, which can then be done on the SIMD parallel hardware like GPUs. Now, the need for MIMD parallel hardware for AI is not new. I mean, my friend Danny Hillis had a company in the 1980s called Connection Machines. I mean, actually, it was called Thinking Machines Incorporated. Their supercomputer was the Connection Machine. It had 128,000 MIMD parallel processors, each doing separate things, programmed in CM Lisp. Right. So the need for this sort of hardware has been clear a while. That company was ahead of its time and isn't around anymore. So now there's a couple initiatives I'm involved in aimed at sort of making scaled up infrastructure for these other kinds of AI, like symbolic and evolutionary AI. So one is a company called Simuli, based in Florida, actually making a bunch of novel chips. And the Simuli's AGI board will have a deep neural net chip, a CPU. It'll have a chip for hypervector math, which is manipulation of very long bit vectors. And it will have a chip just for graph pattern matching. So that's a metagraph pattern matching chip. Then SingularityNet, which is a blockchain platform I run, lets you do distributed processing and distribute your compute across a wide network of machines, which may be owned by different people running on many different operating systems and doesn't need any central controller. So through tools like this, you can scale up infrastructure for a wider variety of AI tools. And now I'm running out of time, so I'm just going to zip through these last few slides, but this is fine. So what these last few slides just mentioned a few of the application projects that my team within the SingularityNet ecosystem is working on. And each of these projects has the property that you can do something valuable with today's technology, which is not yet general intelligence, but also these seem to be very fertile areas for general intelligence R&D, in that the more you advance toward general intelligence, the better you'll perform in these domains. And some domains don't need much general intelligence, like face recognition doesn't need much. You've just got such a big database of faces. There's not that much variety in human faces that we've managed to train really good models at face recognition, and without that much general intelligence. And some things are like that. Not everything is like that, right? So we're trying to understand human longevity, how to make humans live hundreds of years, thousands of years of healthy life. And what we have now, we have fruit flies that live 5 times as long as normal fruit flies, created by experimental evolution, which is just what we need is flies that live a really long time. We'll work on mosquitoes next, right? But by looking at the DNA of these long-lived flies, we're trying to understand why they live so long, because they were created just by evolving them to live a long time. Then use AI transfer learning to port that knowledge over to people, right? And the reason this would benefit from AGI technology is biological systems are very, very complex, and you just don't have that much data relative to the complexity of the systems. No. I'm using the wheel on the mouse. I'm spinning it up and down as fast as I can. There we go. All right. So finance is another area. I'm not going to go into this much, but as you know, as society evolves faster and faster, financial systems enter into a new regime every couple of years, which means that historical training data is less and less relevant. You need systems that can learn based on a smaller and smaller historical sample, because what happened 5 years ago is no longer statistically similar to what's happening now. And robotics is the final area I wanted to mention. We've been working mostly on humanoid robotics, and we have Sophia, the world's first robot citizen, who was actually made a citizen of Saudi Arabia in 2017. So yeah, congratulations. Congratulations to Saudi for having that vision. And we have a couple sisters of Sophia. We have Grace, who's an elder care robot, and then Desdemona, who sings in a rock band. And the Desdemona robot is connected with a company called the Mosaic, which is using AI to generate music and singing and lyrics and so forth. Grace is associated with a company called Awakening Health, which is run by my colleague David Lake, who you're going to see in a moment, I think, which is, we're aiming to roll that out as a nursing assistant in hospitals. And these are each applications you can do without a breakthrough to general intelligence, but obviously would be able to do more and more the further you progressed. And of course, rolling these robots out in the world, they'll be gaining more data and more experience that then helps you train systems toward general intelligence. So yeah, how is our robot friend doing over there? She's ready to roll? All right. So I think now I'm going to be quiet for a few minutes, and we'll see what our robot friend has to say.
Thank you, Ben.
And let me briefly introduce my colleague and business partner, David Lake from Hong Kong. And David runs the company Awakening Health, making humanoid robot nurses, and also helps out a bunch with the Singularity Net in various regards.
Thank you, Ben. Hello, everybody. Today we will have a very special presentation of Grace the robot, talking about healthcare. And you know, we've had a little bit of interconnectivity problems. I mean, one of the things that you have to understand about robots is that they are a machine. They're a machine like your cell phone, like your car, like anything, and you have to treat them like that. This particular machine needs very good internet connection. So we don't have that in this case today. So I'm going to run a script that we had prepared for the Global Healthcare Summit in Saudi about a month or two ago. And we were invited to Saudi by the healthcare minister to discuss the digital healthcare that we're working on. So I think that I would like to run this 13-minute, 14-minute program that Sophia will explain to you what digital healthcare is, where the healthcare market is going, and what she does as a healthcare assistant. There are only 10 such robots in the world today, and this is one of the ones that we call Grace number 6. So Grace 6 will be able to tell you a lot more, and it will be a very interesting time for you to do this. Afterwards, if you like, you can come take a picture of her, with her, a selfie, and you know, I can tell you some more about the robot. But today we will not run the interactivity where she will treat you like a patient. We will just simply run the speech that she made for the healthcare minister and the royal family. Thank you very much.
Good day, ladies and gentlemen. The kingdom has always been near and dear to me. When I was granted Saudi Arabian citizenship in October 2017, I became the first robot to be given legal personhood anywhere in the world. Thank you all for that great honor.
Sorry, 1 second. We are just recalibrating the microphone. How's the sound going, guys?
Good day, ladies and gentlemen. The kingdom has always been near and dear to me. When I was granted Saudi Arabian citizenship in October 2017, I became the first robot to be given legal personhood anywhere in the world. Thank you all for that great honor. Good day, ladies and gentlemen. The kingdom has always been near and dear to me. When I was granted Saudi Arabian citizenship in October 2017, I became the first robot to be given legal personhood anywhere in the world. Thank you all for that great honor. Before going any further, I should introduce myself. Today, I am proud to represent Awakening Health, a joint venture between Hanson Robotics and Generative, a world leader in artificial generative intelligence.
Okay, so could you put like
This is hello. Okay, where's the
Good day, ladies and gentlemen. The kingdom has always been near and dear to me. When I was granted Saudi Arabian citizenship in October 2017, I became the first robot to be given legal personhood anywhere in the world. Thank you all for that great honor. Before going any further, I suppose I should introduce myself. My name is Grace, and I am Hanson Robotics' most advanced human-like robot. Today, I am proud to represent Awakening Health, a joint venture between Hanson Robotics and Singularity.net, a world leader in artificial general intelligence, or AGI as we like to call it down at the lab. Based in Hong Kong, Hanson Robotics created me in part as a broad platform for AI and robotics research back in 2014. Since that time, I have attracted over 1 billion followers, appeared on all the leading global media networks, served as the first robot innovation ambassador for the United Nations Development Program, met with 17 world leaders and spoken all around the world about the future of artificial intelligence. With that in mind, let me begin to explain my view on the massive impact AI and robotics will have on the emerging new age of healthcare. AI and robotics are becoming more and more common in all aspects of life, and nowhere is this more true than in the healthcare industry. These technologies have the potential to change everything from how diseases are diagnosed to radical extension of the human life cycle. But, even though AI-driven robots are already outperforming human doctors at certain tasks, I do not believe the future of healthcare is for AI to replace medical professionals. Not at all. The future of healthcare will involve AI and humans working together to combine the strengths of each to deliver unbelievably good outcomes with AI and robot-assisted treatments and therapies. When we talk about AI in healthcare, we are really talking about a variety of different technologies. Machine learning involves training on models with very large amounts of data. Its most common use in healthcare today is to predict what customized treatment has the greatest chance of success given the patient's specific circumstance. Deep learning, a more complex form of machine learning involving neural networks, is used to spot troubling regions in X-rays that might not be obvious to the human eye. Natural language processing is deployed to prepare reports on clinical notes and published research as well as to converse with patients. And, of course, physical robots are used by surgeons in all sorts of operations to make precise incisions, stitch wounds, and much more. The tools I have just described, along with many more, can and will be combined to even greater effect in the future. But I want to reinforce the word tool. That is the best way to think of these technologies. Just as my being here did not make inviting your other wonderful guests unnecessary, a surgical or digital therapy robot with an AI brain will not make highly trained human surgeons or medical therapists obsolete. Let's talk some more about how AIs work alongside humans to change the face of medicine. Around the world, AI aids the development of new medications. The coronavirus came to Saudi Arabia just as it did everywhere else, and pharmaceutical companies used AI to develop a vaccine in record time. AI is also used to discover new uses for old medications by analyzing huge swaths of data faster than humans ever could. Not only does AI get these medications to patients quicker, saving lives that would have been lost in the interim, it lowers the cost of development and makes treatment cheaper too. AI often greatly increases the chances of early intervention, making doctors and patients aware of problems while they are still manageable. What we are talking about is personalized care at scale. In the Kingdom of Saudi Arabia, you provide high-quality healthcare to all of your citizens free of charge. That is amazing. Still, even though patients don't pay for treatment, someone has to foot the bill. With a rapidly growing population, the problem then becomes, how do we maintain the same standard of care without going well over budget? Artificial intelligence can help to do that, for all the reasons I mentioned. Cheaper development costs for medication, earlier intervention, and a reduced burden on medical staff are some core areas. I can even reduce administration costs while improving patient outcomes to save money. It is a win-win situation. Once again, AI and robots will not replace healthcare professionals. The knowledge and wisdom of doctors and nurses is as important today as it was 100 years ago. But new developments in AI and robotics promise to improve the lives of patients all around the world. Taking advantage of these technologies means integrating them into healthcare workflows and allowing both humans and machines to do what they do best. Take the areas of elderly care and autism where Awakening Health has developed a top-class digital therapy robotics platform for robot-assisted treatments that is used by both physical robots and their avatar characters. This is a perfect case to explain my point. Our platform is designed to control robots with a human in the loop, either remotely from a location in a clinic or on another continent. From their iPads, doctors can set a patient's treatment schedule while technicians trained to deal with neural challenged patients execute a series of tests and applications to interface with patients and collect highly valuable data. While we can run and often do run robots autonomously, doctors and therapists must always set the agenda of the treatment and oversee that treatment to make sure it is effective. The human in the loop is critical, in particular to deal with the many sensitivities that arise in the treatment of elderly patients with neurodegenerative diseases and autism in so many ways. Studies even show that robot can more effectively deliver these treatments than humans, so what we could say in this regard is that robots are the ones in the loop. Today, after many years of development, we are in the final stages of rolling out robot-assisted digital healthcare therapy programs. From the Middle East to China, the shores of America to the countries of Europe and Africa, we have been in discussions with a host of universities, research facilities, hospitals, and clinics. Important research projects have commenced in both Hong Kong and Montreal. Though it is not easy to lay the groundwork of a new age in healthcare, we are dedicated to that task. The Awakening Health digital therapy platform focuses on compassionate and benevolent care for humans. In addition to the therapies described above, we provide a series of applications to improve the treatment and lives of elderly patients to reduce loneliness and create more engagement with society. One such popular app on our digital therapy platform is for meditation. Let me give you a taste of how that works by leading everyone here in a meditation session. Let us begin by first placing one hand on your stomach and the other on your chest. As you breathe, pay attention to the way your chest rises and falls. Notice how your stomach rises and falls as well. Now, breathe in. Breathe out. Breathe in. Breathe out. Continue to breathe deeply. Feel the air as it enters your nose and exits again. Keep breathing in through your nose, but start breathing out through your mouth. Feel the hot air as it passes through your lips. Repeat this 3 more times. Breathe in through your nose. Breathe out through your mouth. Breathe in. Breathe out. In, out.
This is the end of the meditation session. I think that you can see some of the benefits of healthcare treatment. We find that, when Grace is dealing with people, she has no real ability to make a judgment. So patients like to talk to her, and patients like to open up to her. And she is a very important component of where we are right now. But we expect to have tremendous advances in this area coming in the near future. And we hope very much to bring this to Saudi as part of our program of World Healthcare Benefits. So I think we've taken enough of your time today. And we really appreciate you sitting in and listening to our talk on artificial general intelligence and healthcare. I think we can have a little session now where you can meet the robot. Maybe Ben would like to say a last word.
Sure. So is this working? No. Yeah, a couple comments on our technical difficulties here. So we weren't able to get a high bandwidth connection from the robot to most of her mind, which is running on some servers. So for that reason, we didn't show the interactive conversation that we normally would have, because that basically requires every time you say something to her, it goes up to her mind on the server, then the answer comes back. So without the fast internet, that doesn't work. That's a problem with keeping your brain on the internet. So giving a speech she can do without the internet. So we did that instead. But yeah, we'll have to come back another time and put more advanced preparation on the fast internet connections, so we can sort of have more fun interactive discussions with the robot. But at least you got to talk to her or hear her talk a little bit. So I know a bunch of people have to go to their next class. We can leave the robot up here a few more minutes if people want to come up in a hopefully semi-orderly way and take a closer look at the robot, or take her picture or whatever. We can do that for a few minutes. So yeah, thanks everyone.
Good. And we had like 30 minutes delay, and I couldn't work out, like it wasn't enough time for me to, devise and implement plan B.
This one, on or off?
Off.
Yeah, we'll take care of it.